Okay, folks, a quick recap of calorimetry. Remember, this is the third way to find delta H. The first way we talked about finding delta H was using the standard enthalpies of formation. Those were the values found in the big tables. Had a very specific definition. You should make sure you know all that. The second method for finding delta H was using Hess's law, and that had to do with rearranging the chemical equations so we can add them up and go from the prescribed reactants to the prescribed products in the target equation. So this technique for determining delta H depends on experimental data. So that's why we did it in the lab when we took the acid and combined it with magnesium, and then we took the acid and combined it with magnesium oxide. We did the calorimetry and used that to find delta H for those reactions. A few things that you want to make sure that you're aware of. I want to go through the parts of the calorimetry equation pretty carefully. First is this Q, okay? Q is the energy that is transferred, okay? And transferred to the surroundings. We're going to talk a little bit more about that in a bit. So let's say this is energy transferred, okay? It's different than delta H, okay? If you'll recall in class, we said that delta H is like the calories per serving that you would find on the side of a cereal box or, you know, your candy bar or something like that. Q is simply just the energy. It's not the energy per serving like delta H is. It's just energy, okay? How much energy was transferred. We haven't tied it to a particular amount of stuff that's there, okay? But it does depend on these three variables that you see in the equation. All right, let's move from left to right here. The M, okay, just reviewing. I mean, obviously this is mass, but it's the total mass, okay? The total mass of, usually, for our purposes, the water that's in the container. You can see the water down here, okay? And whatever you put in it, okay? So let's say total mass of water plus, let's call reactants, just so it's clear what we mean, okay? All right, that shouldn't be too hard. Watch your significance digits when you're doing the adding. Let's talk about C here. This was something new, okay? C is the specific heat capacity. Sometimes you'll do calculations to find this. And remember, this is a measure of the property of an individual substance. So, for instance, we said that water has a very high specific heat capacity, and something like metal has a very low specific heat capacity. It's the energy required to change 1 gram of the substance by 1 degree Celsius. That's what we mean by specific heat capacity. For water, this is something you should know, it's 4.18 joules per gram degree Celsius. Okay? The last term in the equation, and actually I should have put a delta symbol in front of it, is this T. Really, it's the change in T, so I'm going to make that adjustment here when I write it out. Okay? And that is, we always do final temperature minus initial temperature. And we get that, and we usually do it in degrees C because that's what we have our specific heat given in. You could do it in Kelvin, but that would also, I mean, we'd want to probably change the units of this to reflect that. But for our purposes, I think we're going to stick to degrees Celsius. Okay? One last thing I want to make sure that I underscore is that when we measure this Q value up here, okay, so when we measure this, I'm just going to draw a line down here, an arrow. That's the Q, the energy that was transferred to the surroundings, okay? But when we want to find delta H, we need the Q of the reaction, okay? So whatever the surroundings lost or gained is the opposite of what happened to the reaction. So usually we take and we put a negative sign out in front of this value and say the opposite of the Q surroundings is going to be the Q for the reaction. Okay, and again, that becomes important because when we do the final step in our analysis, we're going to take the Q of the reaction and we're going to divide it by the number of moles, and that's going to give us the delta H, okay, the calories per serving, right? Calories, the energy in the numerator, and per serving, per mole in the denominator, okay? As we go to the next slide, we'll do a little bit of a practice problem and see if we can get you all set on this. Okay, so here's the first question from the home worksheet using calorimetry to determine delta H. I guess the first thing I should probably do is write the chemical equation, but we're talking about taking KCl, okay, the solid, as we have 12.8 grams of it, and we're going to dissolve that into solution. And you may recall that it dissociates. Ooh, there's something to review for the exam if you haven't done it already, that it dissociates into its ions. Okay, so let's get our equation out there. I'll write that down, make sure that we're all ship-shape on that front. So we have Q, and I'm going to make, just to emphasize, I'm going to put that this is Q surroundings, and that's equal to M times C times delta T. Okay, so let's fill in the parts here. Maybe I'll start a new line in my equation. All right, the mass. The mass, we have to add the two together, so maybe I'll show that. We have to take the 12.8 grams of the KCl. I'm going to leave the units out for now just to save a little space, plus the 75 grams of water. Okay. We'll multiply that by the specific heat capacity again, the 4.18. We use that in lab. Just reminded you of that on the previous slide. And then we have to do the temperature change. And remember, we do final minus initial. So in this case, final temperature is 21.6. And the initial temperature was 31.0. Alright, if I do all that and I figure out my significant digits, what I should get is minus 3,500 joules. Okay, 3,500 joules. That's only two significant digits. Remember then, if I'm going to get the Q of the reaction, I have to change the sign. So since Q surroundings is negative, Q reaction, I'm going to have positive 3,500 joules. Okay, so in other words, to get this KCl to dissolve and dissociate, I had to put 3,500 joules in. Alright, now I need to divide by the number of moles, so I'm just going to change colors here to sort of do a side calculation. I have to take my 12.8 grams of the KCl, they show me that in the problem right up here. I have to divide that by the molar mass of KCl, and I should get 0.172 moles. Okay, so we're going to take the 3,500 joules, we're going to divide it by 0.172 moles. Okay, and when we do that, the answer for delta H that we get should be 20.3 kilojoules. Okay. Hopefully you find that helpful in terms of how to solve these problems. Obviously, if you have more questions, we can take care of them in class.